Hello all of you. So, in the last lecture we have been discussing the Lagrange multipliers, that is for maximization with constraints, and we discussed the drunkard-Walk example. So, in today's lecture we will take the idea to distribution of quanta in molecular systems, and later on we will discuss the idea of thermodynamic ensembles. So, to begin with, let us just go back to the example that we have done couple of times in this course already. So, if you have some quanta of energy to be distributed among some particles, let us say you have m quanta among n particles, and again I will emphasize that the particles can be atoms or molecules, whatever is appropriate for the context, and the quanta need not be equally spaced. That means, we can in general say that we have energy levels epsilon naught, epsilon 1, epsilon 2 to some epsilon m. If they were uniformly spaced, then it was like in multiples of epsilon, but this need not be generally true. So, then for this particular problem, we have already established that the number of ways for a particular distribution in which n naught particles have energy epsilon naught, n1 has energy epsilon 1, n2 has energy epsilon 2, and so on. Let us say nm has energy epsilon m, then the number of ways for this particular distribution is given as n factorial divided by n naught factorial, n1 factorial until nm factorial. Now, we have two constraints in this problem. The first constraint is that the sum of these n naught, n1 and so on is equal to the number of particles, and then if I assume the system to be isolated, that means the energy of the system is constant. There is no exchange of energy with the surrounding, and there is no exchange of mass as well, which in this case is the number of molecules. So, in that particular case, there is also a condition for energy, and that is n naught multiplied with epsilon naught plus n1 multiplied with epsilon 1 and so on is equal to some energy E, that is the total energy of the system. Now, in fact, this corresponds to the internal energy, but we will use the word E instead of U that we used earlier. So, E is same as U in our earlier description, and I am doing that because most textbooks on statistical mechanics use E as the representation for the internal energy. So, then we can write this in the shortcut notation, and also keeping in mind that these two constraints have to be met in a shortcut way, and since we do not want to include the constraint in the expression itself of W, we will represent this n as the sum over of n naught, n1 and so on, right. So, the fact that the sum is equal to n is taken care of by the constraint. So, in the equation or the expression for W, we will simply write as sum over the n naught, n1 and so on, right. So, we can write this in the shortcut notation then as sum over nj's factorial, and then there is a product over nj factorials. Keep in mind that this pi symbol is for products over the nj values, in this case n naught factorial multiplied with n1 factorial and so on, and both these things are going from j equal to 0 to m. And then I can also write this constraint in the shortcut notation as let us say G1 is the name of the constraint, then G1 is sum over Nj minus N, although I am not putting in any index in the summation. Keep in mind that whenever I put a summation symbol sigma, it means that we are doing a summation over all possible values of j, that is j equal to 0 to m in this case. Just for simplicity, I will simply use summation symbol, but we always mean summation over all possible values of j or whatever index we have in the problem. Similarly, the second expression can be written as sum over Nj epsilon j minus E is equal to 0. So, essentially in the shortcut notation, the formula is W is sum over Nj factorial by product over Nj factorials, and we have to maximize this. So, we have to find the values of Nj for which this function is maximized. Whenever I put a curly bracket, this is a shortcut for n naught, n1 to nm. Okay. And this subject to two constraints I just wrote, that is G1, that is sum over Nj minus n is equal to 0, and G2, that is sum over Nj epsilon j minus E is equal to 0. Now, as we have noted earlier, we will use the Stirling formula for large n, that says that ln of x factorial for large x is x ln x minus x, and since the maxima of w is going to be the same as maxima of ln of w, because ln of w increases in the same way as w. So, therefore, wherever we have maxima of w, we also have maxima of ln w. So, therefore, I can write the problem instead of this as maximize Nj ln of w, that is ln of summation of Nj factorial by product over Nj factorial, and this becomes, using the Stirling approximation, we can write this as ln over sum of Nj factorial minus sum over j ln of Nj factorial. You can see where we had a product, when I apply the ln, the product becomes the summation when I am using in the log terms, and this is approximated as sum over Nj ln of sum over Nj minus sum over Nj, and minus the same thing for the second term, that is minus Nj ln Nj, and then we have again a summation over Nj. So, clearly this 2 are going to cancel, and what we have is simply summation of Nj ln summation of Nj minus summation of Nj ln Nj, and we have to maximize this with these two constraints. So, the maximization problem then is dou ln w by dou Nj minus some Lagrange multipliers for the first constraint, let us call it lambda 1, dou G1 by dou Nj minus lambda 2 dou G2 by dou Nj, that is equal to 0, and this has to be true for all j. So, let us write this expression. So, you have dou ln w by dou Nj, since ln w is equal to summation of nj ln summation of nj minus summation of nj ln nj. So, the dou ln w by dou nj becomes, for the first term, summation of nj and the derivative of log, that is summation of nj, and the derivative of summation of nj with respect to nj. So, for all the values of j not equal to the j with which I am finding derivative, the derivative is going to be 0. Only for that particular value of j at which I am finding derivative, it will be equal to 1, right. So, this is the derivative of summation with respect to nj. Just for example sake, let us say if you have the summation written like this, and if I want to find derivative with respect to n2, that is I am doing with this for j equal to 2. So, in that case the derivative of n naught with respect to n2 is 0, derivative of n1 with respect to n2 is 0, only the derivative of n2 with respect to n2 is equal to 1, and therefore, we have a 1 there. Now, similarly, we have summation of the log of the summation of nj, and again we are taking derivative of summation of nj with respect to nj, that is again equal to 1, and the same thing I am doing for the second term, and now it is summation over nj ln nj. For all the other values of j not equal to the particular value, the derivative is equal to 0. So, therefore, we only take derivative for that particular value of j, and that is nj by nj minus ln of nj. So, I hope that is clear. So, then these two cancels out, and what we have is essentially minus ln nj by summation of nj. Now, there are two other derivatives here, that is dou g1 by dou nj, and g1 in our case is summation of nj minus n is equal to 0. The same rule applies there. For the summation over nj, only one of the nj value will remain for which I am taking derivative, and that is equal to 1. And similarly, dou g2 by dou nj, where g2 is nj epsilon j minus e is equal to 0, this gives me epsilon j. So, therefore, the minimization expression that we have dou ln w by dou nj minus lambda 1 dou g1 by dou nj minus lambda 2 dou g2 by dou nj is equal to 0. This becomes then minus ln nj by summation over nj minus lambda 1 multiplied with 1 minus lambda 2 epsilon j is equal to 0. Now, this expression I can write as an exponential because I can move ln to the other side, and therefore, what we get is nj by summation over nj is exponential of minus lambda 1 minus lambda 2 epsilon j. That is the most probable distribution in this case, for which the ln w is maximized. Now, we can use the constraints again to find the Lagrange multiplier lambda 1, and that is, since we know that summation of nj is equal to n, what we can do, I can apply summation on the both left hand side and to the right hand side. So, what we then have is summation of nj by summation of nj. So, clearly the summation applies to the numerator, the denominator is already a sum. So, basically this becomes 1, that is summation over j exponential of minus lambda 1 minus lambda 2 epsilon j. Now, lambda 1 is a constant for all values of j. So, I can pretty much move exponential of minus lambda 1 outside. So, you have exponential of minus lambda 1 summation of exponential of minus lambda 2 epsilon j, and therefore, what we have is exponential of minus lambda 1 is equal to 1 over summation of exponential of minus lambda 2 epsilon j, and this if I put back right here, what we get is exponential of minus lambda 2 epsilon j by summation of exponential of minus lambda 2 epsilon j. So, the result that we have got is actually similar to the Boltzmann distribution that we have obtained earlier. So, what we have found earlier or what we have used earlier is that I said that the number of the molecules in a state j or having energy epsilon j is proportional to exponential of minus epsilon j by kBt. So, if I compare this expression with that expression, so the denominator is a summation. So, whatever we have here should apply to the numerator, and what we should find then is lambda 2 is equal to 1 over kBt, which is referred as beta in statistical mechanics, right. So, it turns out that the example that I have taken where the system is isolated and it has some number of molecules, and since I was not doing any work as well, although I did not state that, the volume is also constant, and in fact, at most probable distribution the entropy is also constant, right. But the other way to say that is that the energy is constant. So, I can write energy as a function of entropy, or I can write entropy as a function of energy. So, what we can say then here is that for this particular case, entropy can be thought of as a thermodynamic function and n, that is the number of molecules, V, that is the volume, and E, that is the internal energy of the entire system, are the control variables. Now, if I think of a system that has a constant number of molecules, constant volume and constant energy, then there is not only one system that is possible for this particular scenarios. You can have various distribution of quanta of energy that will still give you the same total energy. So, whenever we are talking about a system in thermodynamics, actually we are not talking about one particular configuration or one particular distribution of energy, we are talking about a whole ensemble of distribution, right. So, essentially we can imagine that we have many systems that are present which are having same NV and E. So, all of them can have same NVE, but they can have different energy distribution or even the position of molecules among there, and all of them will refer to the same system at NVE. The other way to think about it is, let us say if I specify that this room is in equilibrium and we have certain properties. Now, the molecules in the room are not frozen, the molecules keep on moving. So, therefore, when I specify the thermodynamics of this room, I am not interested in a particular configuration, that is like a snapshot taken at a particular instant, but an average over many conformations that is going to be realized over a period of time. The other way to look at it is that if the room is in equilibrium, I can think of like small volumes of the room which are having same property at every other volume, because the property of the room property of the air in the room should not change if I go from here to there. If it does, then the room is not in equilibrium. When we are in equilibrium, then the properties of every particular small volume remains the same. So, when we think of an ensemble, we can think of it as a collection of states either at different time instants or at different spatial locations. And whenever we talk about any property in thermodynamics, it is always an average over many possible states of the system having the same value of control variables, in this case n, v and e, but different possible configuration and different possible distribution of energies, right. That is a very important point that we will build on. And in this particular case, where I am keeping the n, v and e constant, is referred as a microcanonical NVE ensemble. And the ensemble will comprise of some A states and any property A states or A systems, to be more precise. So, now I am not talking about the state of a molecule, I am talking about the state of the entire system. So, you can have multiple configurations of the system which are present at this NVE. We can think in terms of different time instants or we can think in terms of different spatial locations, but nonetheless whenever we are doing thermodynamics, we are essentially interested in the average over all those possible states and systems, right. Now, you can clearly imagine that the number of possible states are going to be huge. So, it may go for large molecules something like infinity, right. So, this may be more like a theoretical construct than being like a complete enumeration of all possible states. So, A in theoretically speaking should represent all possible states of system, but we need to make certain approximations if I want to represent the system with fewer number of states, right. So, because we cannot do like infinite possible states and compute the average, that is not quite possible, and therefore, we will enumerate some of these states. So, we can approximate the ensemble for some possible states or systems, but in reality the number of systems or number of states can be huge. So, A can be really a very huge number. And then what we are also assuming is that all these systems are isolated. So, although they are present in a box that I am showing, there is no interaction between system, there is no exchange of mass or exchange of energy between different systems in this case, because we are doing a NVE ensemble which refers to an isolated system as we discussed. Okay. So, this is, it turns out that this is not a very useful ensemble for many applications, and the reasons we have stated earlier, that it is not always possible to control entropy or the volume. Sometimes it is more appropriate, actually experimentally it is always more appropriate to control temperature as opposed to entropy, but sometimes it can be also appropriate to control pressure instead of volume, and therefore, we can have a variety of ensembles, and the ensembles are defined on the basis of what is the control variable in the particular case. So, we will discuss in this course 4 different ensembles which are most commonly used, which will have different set of control variables and therefore, different thermodynamic functions representing them. And these are the one that we already have discussed, the microcanonical ensemble, and in this case the control variables are number of molecules, volume and the energy, and thermodynamic function is S n V E. We can write in differential form ds is equal to dE by T plus PdV by T minus sum over mu j by T d and j. We can also have something called a canonical ensemble. In that case, the control variables are n, v and t, number of molecules, volume and temperature. And in this case, the thermodynamic function is called the Helmholtz free energy, that is a function of n, v and t, and the differential form is df is equal to minus s dt minus pdv plus sum over j mu j d and j. By the way, we are doing for multi-component systems in this case. If it is a one component system, then the last term with chemical potentials will not appear. And then we can have something called an isothermal isobaric ensemble, and in this case NPT is constant, the number of molecules, pressure and temperature, and in that case the thermodynamic function we are interested in is the Gibbs free energy NPT. In differential form it is dG is minus S dt plus V dP plus summation of mu j d and j, and the last one is the grand canonical ensemble, and in that case the control variables are mu v t, that is the chemical potential, volume and temperature, and we can define a grand canonical potential, that is a function of mu v t, that is d omega is equal to minus s dt minus p dv minus sum over n j d mu j. One thing to note here is that in all these cases I have kept at least one extensive variable, right. In this case both n and v and e, all of them are extensive. In this case n and v are extensive, in this case n is extensive, and in this case v is extensive. There is nothing called a mu pt ensemble, because then all the variables become intensive, and we have earlier said using the Gibbs duhem theorem that that does not give me a meaningful differential form, it becomes 0. You must have at least one extensive variable, because something in the system, something about the system should specify the size of the system. So, with that I conclude the discussion of thermodynamic ensembles. In the next few lectures we will show that how can we find thermodynamic properties for all these ensembles by first defining the ensembles, then defining the function that we have to maximize and then or minimize, and then finally using the method of Lagrange multipliers we can determine the average properties for the ensemble, and whenever we talk about an average, it is average over all the systems present in the ensemble. So, with this I conclude the discussion here. Thank you.